Okie dokie. In this video lesson, we'll be looking at the transformations of the graphs of sine and cosine. So we'll review the two forms, the general forms of sinusoidal functions, or the two different sinusoidal functions that we've looked at so far as y equals a sine bx minus c plus d and y equals a cosine bx minus c plus d. We've already looked at what each of the different variables represented. Specifically, we saw that the A that represented the amplitude, while the B helped us determine the period by taking 2 pi and dividing by B. And then we jumped to the D. The D represented our midline. So what we'll first do is look at how does the amplitude impact the graph of sine and cosine. So we'll go to this graphing calculator, and here's our general form. There's the A. Right now, A is 1. And we see that as our amplitude changes or goes up, it begins to stretch. So that's the transformation that occurs as the amplitude is changed. So as it gets higher, it stretches. As it gets lower, meaning between 0 and 1, I should say 1 and 0, it begins to compress or shrink. So, and if we went into the negative side, our picture reflects. So the negative reflects, but as soon as I go to the other side, the positive, it goes back. So the amplitude, or the A, impacts the graph by way of a stretch or a compression vertically. So A impacts the transformation by being a vertical stretch or compression. And if A was negative, it would reflect about the x-axis. So let's go focus on B now. Yes, we know B, if we applied with 2 pi, we can find the period. But here's our B. Right now it's 1. So as I begin to change, it begins to compress and stretch. So that's what's occurring. The B is causing the graph to stretch out and to compress. So we'll look a little closer. Right now, let's put the B at the 1. And as B gets larger, it looks like it's compressing or shrinking. As B gets smaller, it's stretching out. So we see there's a kind of a backwards correlation. You would expect as it gets higher, it should stretch, but actually what's happening is this. Normally, when B was at 1, if I can get it there, there we go. When B was at 1, our period was 2 pi. So it's saying one complete cycle occurs during this normal distance, the normal distance of 2 pi. But as I increase B, let's just put B at 2. When B is 2, we see that, yes, it looks like it compressed, but from here to here is one cycle, here to here is a second cycle. So what that 2 is telling us is that we're going to have 2 complete cycles within that normal distance of 2 pi. So if you were trying to put double the amount inside of this one space, that's why it has the effect of shrinking or compressing the entire graph. So again, with B, there's this counterintuitiveness. As B gets higher, it begins to compress because more cycles are being placed inside that one distance. But as B gets lower, lower than 1, it begins to stretch out. So if I put it at 1/2, 0.5, oops, if I can get it there, there we go. As you can see now, from our normal distance from 0 to 2 pi, only half the graph is actually in that distance. So we can see the correlation between the number and what it actually represents in the graph. So when B was between 0 and 1, there was a stretching. When B got greater than 1, there was a compressor. So we see B creates this horizontal stretch and compression. When b was greater than 1, we just saw that there's a compression because more periods or more cycles are being placed in that same distance between 0 and 2 pi. If b was being between 0 and 1, we just saw that there was this stretching because less of the picture has to fit within that distance of 0 and 2 pi. So let's look at the d, this midline. So back to our formula there. There's the d. Right now, if I move the d, there's our midline changing. So as d goes up, the entire graph is shifted or translated up. As it goes down, the inverse. So this is more direct. So when I go back, we can see that the midline, or d causes a vertical shift or vertical translation. So now we'll bring our attention to the C. Right now it says a horizontal shift. Well, if we look at all the other transformations, this was a vertical stretch, horizontal stretch, and compression. Well, this was a horizontal shift. I'm sorry, vertical shift. And the only thing left was a horizontal shift. Well, let's confirm. If I just change my C, there's my C, so I change it. As C goes up, the picture tends to go to the left. So it's kind of doing just the opposite of what you would have thought. As C gets smaller or moves to the left on the number line, the actual picture moves to the right. So there's this backwards effect with the C. But what we do see is that it does impact the graph by shifting or translating left and right or horizontally. So in our PowerPoint, there's our C, horizontal shift. Now there's something we need to look at a little closer with respect to movement horizontally. What I'm getting at is that it was both the B and the C that impacted our graph horizontally, whether it was a horizontal shift or horizontal compression. So when we consider both things that impact horizontally, we're looking at something called, yep, it did go in the opposite direction, forgot about that, something called phase shift. So the next slide will kind of look a little closer at this concept of phase shift, where we're considering both the B and the C. So if we went back to our normal graph of y equals sine x, we just saw that several things can happen horizontally. Well, I could compress it. So there's our B. B got higher, so therefore there was this compression. So there's some horizontal movement. But in addition to this, so right now, B was 2. So the period was 2 pi over B, which means our period was pi. And we can see that distance was pi. And it did impact what was happening horizontally. So again, this is why I'm talking about the B in this conversation. But now we consider, well, if I compressed it and I also moved it or shifted it or translated it horizontally. In this case, if I just move everything to the left, we end up with a combination of things happening, meaning a combination of horizontally shifting and horizontally compressing. So this graph right here is the graph of 2x plus pi over 2. There's the 2 as the b. 2 pi over 2 still gives us that period of 1 pi. The way we can determine that it did shift to the left, we can see it physically moves to the left pi over 4. So the arithmetic to get us to that number, there's a formula for phase shift. Okay, we got our B, we have our C, and the formula for phase shift is negative C over B, which essentially says change the sign of the C and then divide by the B. Again, change the sign of the C and then divide by the B. And that will indicate what your phase shift is. So this will help, I guess in one clean swoop, determine where your graph actually will begin. So if I do the math, there's my change the sign of the C, divide by the B. Gives me negative pi over 4. Hey, that's where we were. But what this actually says is the entire picture moved left pi over 4 units. Again, phase shift, negative C over B, whatever you get will indicate the movement that occurred. So if I look at a couple examples, I've got sine of x over 4 plus pi over 2. And all I'm going to focus here is just the phase shift. So if my b is 1/4, my c is pi over 2. Negative c over b is the formula. So when I take my two values and divide, I end up with negative 2 pi. So therefore, this is telling me the entire picture shifted left 2 pi units. Now, if I look a little closer, because the b is 1/4 and 1/4 is less than 1, we saw earlier that this will result in a stretch. And the vernacular is a horizontal stretch with a factor of 4. And this might be counterintuitive. You're like, well, in the entire equation, b was 1/4. Well, if we look at what's in brown here, when we divide those two numbers, we actually multiply by its reciprocal. So multiplying by 4 creates a factor of 4. I'll do it a few more times in these next two examples. So we've got cosine 2 theta minus 3 pi. We got our b and our c. And when we change the sign of c, divide by the b. So that gives us 3 pi divided by 2. Our final result, 3 pi over 2. So there's our phase shift. Right 3 pi over 2 units. And because the b was a 2, 2 is greater than 1, that creates this compression. Again, by a factor of 1/2. Again, because here, when we actually do the math, we multiply by the reciprocal. And that multiplying by 2 creates a factor of, multiplying by 1/2 creates a factor of 1/2. And the last one, we have our b and our c. Formula, change the sign of the c, divide by the b. So, changing the sign, 5 pi over 6 divided by 1/6 gives an answer 5 pi. So the phase shift, we're moving right 5 pi units. Looking closer at the b, because the b was 1/6, and that's less than 1, that creates another stretch. A stretch by a factor of 6, because there's the 1/6. That means when we multiply, we're multiplying by 6, which means a factor of 6. In the next slides, next video lesson, I'll do some examples. So hopefully this helps get us initiated with the various transformations associated with the graphs of sine and cosine.